Okay, we want to continue the tutorial for logical and relational expressions. And this is the question that we have. It says that the tank in the water tower has a geometry as shown in the figure below. Inside the tank, there is a float that indicates the level of the water. Write a MATLAB program that determines the volume of the water in the tank from the position, that's the height of the float. The program asks the user to enter the value of the height in meters, and as an output to display the volume of the water in meter cube. Realize that we have this particular geometry, and at the base here, it's a fixed cross-sectional area, so it's very easy to calculate the volume. But as you cross the 19-meter mark, realize that the geometry starts to change a bit. The diameter starts to increase until it gets to 46. So that means that the volume that we are going to calculate will also be changing with respect to height, right? So for us to calculate the volume at the top, it's going to be a different thing altogether. And we are working with logical and relational expressions. So what we are going to do is that if the height that the user enters falls below the 19-meter mark, then we can easily calculate it using one formula. But if it goes above, then there has to be another way that we are going to calculate it. So let's get into the math, and then we'll get into the MATLAB script itself. So for this question, the user has to take note of the fact that the geometry at the lower end of the tank has a fixed diameter. But after a height of 19 meters, the diameter is going to change. And this changing diameter is going to result in a change in volume above the 19-meter reference point. So for our MATLAB code, we want the user to enter the value of the height of the float, and then the volume of the tank should be calculated. So we're going to break it up into two situations. If the height that is specified is up to the 19-meter mark, then we can easily find the area of the first geometry, what we've highlighted in red here. So this is what we are going to call geometry 1. We can easily find the volume of, so those supposed to be volume. We can easily find the volume of that geometry. Then if it is more, then we can easily find the volume for geometry 2. So geometry 2 is going to be above the 19-meter mark, but it's still going to be that cylindrical portion of the tank. Then geometry 3 and 4, that's what we are going to label these ends, the ends that were, let me show it here. So the ends that are remaining after we've calculated for geometry 2, 3 and 4 is going to be those triangular portions. And when we put them together, we will get a cone, we'll get a conical shape. So I'll show us an animation to see that as well. So let's analyze the various dimensions we have, and then we'll get into it. This was the base diameter we had. It was 25 meters. We had a height up to that point to be 19 meters. So all the distances here are in meters. And then at the very top, the diameter was 46 meters. So now if the base here is 25, then what it means is that this portion as well should also be 25. So we can get the excess. So 46 minus 25 will give us 21. And we can divide it by 2 to get what is left at both the left and the right hand sides. Okay. Then we can also, this h here is going to represent the height that the user is going to specify. So if the user specifies a height up to 19 meters, you know what to do. And if the height is beyond 19 meters, there has to be a way to go about it as well. Then this is going to be, this L here is going to be the distance from the 19-meter mark upward. So let's see the height the user specifies is 22, right? 22 minus 19 will give us 3. So we are saying that L is just 3 meters above the 19 mark. L is just h minus 19 when h is more than the value of 19. Then we have r, the distance from the center just to the end here. That's what we are going to label as r. So that's going to be the radius, right, from the base. Then we have another one we are going to call RC. This is going to be the radius for the cone, the conical part when we put it together. So that's going to be what we call RC. So the distance from this point to the edge here. Now, if our height is up to 90 meters, then our volume V1 is going to be this portion here. And we can calculate it with pi r square h, right? If our height is more than the 90 meters, then our volume is going to be there. So let me do it like this. Let me erase the ink and do it this way. So let's say our height is more than 90 meters. Let's say it's 22 meters, and the 22-meter mark is somewhere here, right? It's somewhere here. Then what's going to happen is, in effect, so let's eliminate this entire region. We're not going to consider this entire region because we are not there yet. What's going to happen is that then our V2 is going to be this portion here. This whole region down here is going to be our V2. right? So we can calculate that with pi r square h. Then you realize that these small portions here are going to form a triangular region. So those parts are going to be the parts that we use to find the volume for the cone. So what we're trying to say is that when we are more than the 90-meter mark, we can calculate V2 with the animation we saw earlier. V2 is going to be just the cylindrical part, and then VC, the volume of the cone, right? So that's how we would go about it. So for V2 to be pi r square h, depending on the h value we are given, and then for VC is going to be 1 over 3 pi rc squared L. So that RC would be changing based on our height, based on the height that we are going to be working with. So we are saying here that if L would increase, RC is also going to increase. So if we look at it, realize that as my L is increasing, right, the size of RC is going to become larger. Initially it was somewhere down here, right? So the radius of the cone is going to be dependent on the height that we are going to have. So we have to find a way to relate the height we are having to the radius as well. So we have the, if we take the conical part, right, just the triangular part here, and we pick that part out with its dimensions, this is what we are going to get. So we had the base here to be 10.5. We had this side, the maximum that we can get for that side is 14 from the question, right? And then we have our RC, and we also have our L, and then we have the angles as well. So the angle here is going to be the same as the angle there. Now, before we continue, I just wanted to show us the animation so that we can see how it's going to become a cone. So that's how we had a triangular portion, right? And then if we add the other triangular portion, it's going to end up being a cone. So if we had just cut it and we had just looked at it from the front, we would have seen it to be just a triangular portion this way. So you realize that we can see the triangle here and then the triangle here as well. So that's what we are going to see. But because it's a three-dimensional shape that we are cutting and putting together, it is actually going to be conical at the end of the day. So that's what I wanted to show us. Okay, so we can get into the rest of the calculations now. Okay, okay. So we can get into the rest of the calculations. So this is what we have. And we know that if we are looking at this in terms of geometry, tan theta is going to be 14 over 10.5, which is the same as L over RC, right? So for a cone, the volume is 1 over 3 pi r squared L. Then I can also say that because the volume is going to be changing with both radius and height, I'll have to find a way to replace the two of them and replace it into the volume expression, or place it into the volume expression. So what I'm just trying to say is that in the volume expression, we have radius, we have height. Volume is dependent on both of them. But then we are looking at the fact that both radius and height are changing. So when height changes, radius changes, right? So we want to relate them to each other so that we can replace one of the terms here with the other. So we can easily say from this expression here that L is equal to 14 over 10.5 RC. And I can put that into the volume expression so that I would get this expression here. So I've taken the L we had and I've replaced it over here so that I'll get this form of the expression. And if I simplify, I'll get 14 over 3 times 10.5 pi RC cube. Okay, so I want to find an expression for how VC, that's the volume of the cone, is going to change with the radius of the cone. So if we differentiate, the VC, the RC is going to be equal to 14 over 10.5 times pi RC squared. Okay, then I can just say that the VC is equal to 14 over 10.5 pi RC squared, the RC, and I can integrate both sides with appropriate limits so that I can get the volume of the cone. So for the limits, we know that it's going to be from 0 to the volume of the cone that we are having, and from 0 to the radius of the cone that we are having. But we can let MATLAB handle this part easily. And once we find our volume of the cone, we can add it to V2. That's the volume we calculated earlier for just the cylindrical part, so that we can get our total volume. But remember that we are looking at logical and relational expressions. So as I said at the beginning, we are going to use our if functions to determine the volume up to the 90-meter mark. then above the 90-meter mark as well. And we can also include a case for if the user should specify a value more than what our system would allow, right? So that it will display an error message. So we'll move to MATLAB very soon, but then this is just a sample of the code. I'll explain the various parts of it and then we'll just switch into MATLAB and try it out ourselves. So here, this is where the user, line 2 is where the user is going to input the value of the height. And we had the diameter for the base to be 25, so I use that to find the radius. And this is where our relational um, operations are coming in, right? So you're saying that if h is less than or equal to 19, then our volume is going to be pi r square h. So that's just going to be for geometry 1. That's the base here, right? So it will give us the output. It will tell us that the volume of the tank is whatever value we calculated in meter cube. Then if h is greater than 19 and h is less than 33, so 33 is the maximum height, but remember from here to here was 19 and then from here to here was 14, so the maximum height possible is 19 plus 14, which is 33. Then our L, remember we said L was equal to h minus 19. So if we are more than the 19 mark, let's say we are somewhere here, and then this is maybe 22, right? We said that the L here, this L value here is going to be the h, which is 19. Sorry, the h, which is 22 minus 19, so that the L becomes 3, right? And then V1, what we are calling V1 is going to be pi r squared h. So V1 is actually what we labeled as V2 earlier. So let's say that we have it up to this point here, right? So the V1 is going to calculate the volume of this whole region using pi r square h. Then we have the radius relation where we related it to L, and then the angle where we said tan theta was equal to the um, I'm talking about 10.5 and 14. So tan theta was equal to 14 over the 10.5, right? So that we can get the RC, that's extra, the radius of the cone over there. Okay. Then the next part of the code is now the part where we want to write out the differential equation and solve it. But before we get to line 13, we have to start from line 23. So we are going to define the function that would be used for the um, integration of the differential equation. So we can call our function dvdr, and we are going to name it, the output is dvdr, and we are going to name it for and then for the input you are going to have r and v. So remember, when you're working with a function file, you first put the independent variable, then comma the dependent variable. So we write out the dvdr expression, the differential expression. Then we can now come back to line 13 and then do the solving. So we know the v span, that's going to be the range of values for our volume, right? um when it was supposed to be for the radius, so the r span will be from 0 to the maximum radius we can get, right? Or to the, yes, the maximum radius we can get, that's going to be the rc that we have specified. It's going to integrate it from 0 to that point, and our initial condition is going to be 0. So when our radius is 0, our volume is 0, right? So when our radius is 0, yes, our volume is going to be 0. So we can write our ODE expression. So we say that r comma v is equal to ODE 45 at the function name, then v span comma ic. So this is going to be the values for the radius, and then this is going to be the initial condition. So yes, you can use any variable to represent it. I type v span, you can type r span or anything. Just make sure that you are not mixing up your parameters. So then for v2, we are going to sum all the volumes it gets. The reason why we are doing this is because when MATLAB solves this differential equation, right, when it solves the function over here to get a values, it's going to get the values at different points. But because it's an integral, we want to sum all the values that we are going to get. So we'll use sum v. So all the values that MATLAB is going to generate within our span, right, is going to sum all these values together to get the actual volume. So it's like I have a curve, and the MATLAB is just giving me values at one place. I want to actually get the area under the curve. So what do? I sum all the individual portions that I am going to get. That's why we're using the sum function. Otherwise, we're just going to get the individual portions and we won't end up getting the entire value under the curve. Right, so we use the sum function that sums all those values. So we would look at it when we move into MATLAB. Then we can see that the total volume is going to be V1 plus V2. So V1 is going to be the volume for the cylindrical portion, and V2 is going to be the volume for the conical side that we have summed together. Right, so we'll move into MATLAB and then we'll try that out. And let's open a new script. So as usual, we'll start with CLC and clear all. What we are saying is we want to start with our input. So our age is going to be our input. And then you can tell the user to enter the height in meters. Then we have our original diameter, which was 25. We can guess the radius from that, which is going to be that over 2, a diameter over 2. Okay. Then what we can say is that if our height is less than or equal to 19, then our volume, so this time I'll use the symbols we use in the slide. So V1 is equal to pi times our r is r squared. So let me put it into a bracket. R squared times that h value that we had. And then we can just maybe just display the value. So f print f, and then see that the volume is then percent f meter cube, and then we can write the value here. So for the volume, okay. Then we can also say that else if our h is greater, so our h is greater than 19 and our h is less than 33, right? Then we can have our L value. So we said that L was equal to our h minus 19, that part above there. And then we also had a relation between our radius of the cone and L. So RC was equal to L times 10 over, was 10.5 over 14. So this was our RC. Then we can decide we want to calculate for V2. So V2 was equal to pi times R squared pi times r squared times h. For this part, you don't necessarily need to do the dots expressions because it's just singleton, but then just to, because we'll get to a point where it would become necessary, so we are just placing it in, but then we don't need to. If we don't bring it here, it would still run and give us what we are looking for. So we can calculate the volume 2, right, the cylindrical part. Now before we continue, we would now go down and now rather define our function file before we come back. We can say that function the VDR is equal to maybe volume, independent variable, dependent variable, and I can define it. So the VDR is equal to 14 over 10.5 times pi times r squared. So the r that we are going to enter, and I realized that okay, we have r up here, so we can't use the same r down here. So in order to avoid conflict, let me put c here, so it becomes r c. I can suppress and type end. Oh, we also have rc here, so I can put rc here. So let me say let me just make this rp just for the sake of our calculation purposes. Okay, then I can type it. So now that I've defined the function, I want to solve the function. So how do we solve the function? I need to have a span, an initial condition, and then the OD45 expression. So for my span, I can see that my R span is equal to, my radius is going to start from 0 and end at RC, whatever RC value I have. Then I can have my initial conditions also be equal to 0 because it's going to, when R is 0, the initial volume is 0. And then I can now say that my RD comma my V, so independent and then dependent, is equal to ODE45 at the function name, the span, and then the initial condition. So before we continue, let's look at something. So if I should run this, oh, a minute. Let me see where this problem is coming from. Yes, it's because we have an if function here we've not ended. So it's saying that we can't place a function down this way. So let me type end here and then let me try to continue. Let me try and do this again. Okay, so now we can enter the height. So because we didn't end the if function earlier. So let's enter a height more than 19. So let me say 23, right? And now let's look for all the v values so that you understand what I was trying to say. Letter matter is going to get values at different points, right? And if you want to find um the actual volume, then we have to find the sum of all these individual points. So we can say that our v is equal to, or let me say sum of v. So if I sum all of this, it's going to give me that actual volume. So that's how integration works sometimes. It finds the values at different points on your curve. And if you want the actual value, you can just sum everything together. So I can say that my VC, that's the volume of my cone, is equal to sum V. And then I can now say that my V total is going to be equal to V2 plus my VC. And that's it. I can display my output. So F print F. So the volume is percent F. And then say, oh no, meter cube. And then this is slash N. Then I can put here my V total. Now I can also continue and say that else, so let me remove the end from here and say that else if, so let's say the person enters a value more than 33, so if h is greater than 33, right, we can let it display an error. So you can see that maybe an error message, so error, then value is out of range. So now let's try, no, it's supposed to end it. I'm not making the same mistake twice. So now if we should run it, I enter a height less than 90, so maybe 17, it gives me the volume. If I should try running it again, this time I'll enter a height more than 19, so let's say 20. Oh, let me see. Oh, a minute. Okay, I used the wrong slash. This is f print f. So some of these little things can cause a lot of issues. Now let's try it one more time. I enter a value of 20 and it's able to calculate the volume for me. Now let's enter a value more than 20 and more than the 33. So let me enter 35. It displays an error message that the value is out of the range. So this is how we go about this particular question. Okay, thank you very much.